So yeah, welcome to this second session on differential geometry. Today we'll be covering a few more advanced topics, mostly the notions of covariant derivative, parallel transport, and geodesics. I said I was going to also talk about curvature, but I don't have a good, nice, clear explanation and intuition of curvature to give you, and there's only quite a lot of ugly formulas and calculations in this, so I figured we would talk about curvature another day. But yeah, to give you the very high level view, what we're going to talk about today is this notion of, okay, if we have some kind of curve or path that we're following along a manifold, how do we convert objects defined locally, for example, a tangent vector or some kind of a vector in a tangent space at some point, and how does it move, or how did this deform as we go further along the curve? And so there's this notion that we have these tangent space at every point of the manifold, and we need a way sometimes to translate between them, between two different vector spaces, and that's basically what we'll be talking about. But in doing so, we'll be actually unlocking the ability to define a whole bunch of stuff that are actually useful not only when you work with manifold as a mathematician, but for deep learning. So if you had a quick look at the blog post I posted earlier, that's sort of a sneak peek. So since it's been 2 weeks now, I'll give a brief rundown of the notation and some of the stuff we talked about last time. So if you remember, we had a manifold that was just a set of points, such that for any particular point we could define like a local coordinate system that looks like Euclidean space, but it might not be a global coordinate system. We might need multiple coordinate systems and sort of patch them all over the manifold. And within these local coordinate systems, we could also talk about like infinitesimal displacements in one direction in this coordinate system, and that's essentially gives us a tangent space of all the possible displacements. You could also think of it as literally the tangent vectors. Like if you think of the manifold as a geometric object that's embedded in some real Euclidean space, then the tangent space is just the set of tangent vectors at that point. So because we have this like local coordinate system, it induces a tangent space basis on our tangent space. Unfortunately, because we only have this coordinate system, it's very rare that this induced basis, which is the natural basis for the tangent space, is orthogonal. So in general, we'll have some to worry about converting between non-orthogonal vector spaces or vector bases. Another thing is that, okay, we can express not only tangent vectors, but in general we can talk about vector fields, so functions from the manifold that at each point send output a tangent vector at that point on the manifold. And so generally we denote them in this notation as xi. So the xi are like function that determine the coordinates at point I, at the point P of this tangent vector, and these ei's are just the essentially the basis of our vector spaces. We also had, at least on Riemannian manifold, something called a local inner product on these tangent spaces that was simply defined in terms of this object G called the Riemannian metric, which again, because most of the time we have a basis that is not orthogonal, this object here will not be a nice matrix. It will be a matrix that we'll have to invert to be able to perform things. But yeah, and okay, I'm avoiding calling it a matrix because really it's a two form or a O2 tensor that takes two vectors and outputs a scalar, and so it can be expressed as some kind of gij, where these are the coordinates, and these are the induced basis vectors on the dual space of the tangent space. So far so good. Also, just in case, we typically use this Einstein summation that whenever we have like an expression with multiple indices on the top and on the bottom, if the same index appears on the top and the bottom, it means we are summing along it. So do keep that in mind, that it keeps notation concise, but if you're not remembering that it should be a sum, then now is the time to remember about it. Also, again, don't hesitate to interrupt it at any time. Okay, so I figured I'd give an example, and it's the classical example of the metric on a sphere. So roughly we're starting with the sphere defined by x squared plus y squared plus z squared is equal to r squared. So r is just our radius, the radius of the sphere. And so here we are in a three-dimensional space. And we can get coordinates on the sphere using spherical coordinates, so taking an angle theta and phi. And these gives us the points of on the sphere indexed by these theta and phi angles. And so I think if you want a drawing, this is pretty terrible. So this is the sphere. Like let's say you have a line going through the north-south pole, then like theta will be the angle on the, so essentially the longitude, and phi will be the latitude, and it's going to be the angle between the point and the the polar axis. So now to actually express this metric, we can always start with the Euclidean metric, right? Because this is embedded in the Euclidean space. The metric, which is simply the infinitesimal norm element, so the norm of like an infinitesimal displacement, it's simply going to be basically the Euclidean norm. So expressed as dx squared plus dy squared plus dz squared. And the trick, if you want to get back to our coordinates, is to simply use some standard calculus formulas. So here we're taking like this dx squared, expressing in terms of d theta using the chain rule, and same thing for the d phi, and squaring that, and then we're doing the same for dy and dz. And if we chug along and just do the computation, we get some expression with sinus and phi, and so when we square them, turns out we get some simplification, right? Because we get like the square of a difference and the square of a sum, and as luck would have it, like these two terms from the sum, they cancel out, and we're left with these terms in d theta squared that have these like sine theta squared plus cos theta squared in there, and so these two add up to get 1, and so we end up with r squared sine theta phi, so sinus squared of theta times d theta squared. I said theta here, but it should be phi. And similarly with the d phi squared, we get a similar simplification, and we get r squared d phi squared. And roughly, like, the reason it's sort of a translation of what it means to translate like this infinitesimal displacement. We're just changing the coordinates. And so this is an example of a metric. It's the metric on the sphere, and you could imagine this. Notice that here the only elements are d theta squared and d phi squared, so this is still a nice metric because it's diagonal in some sense. There is no like cross elements, so like g, you can still think of it as a diagonal matrix, and so it's easy to invert. So that was the example. We'll keep using that example as we go along, but let's move on. So the main thing that we're trying to do here is to extend the notion of a directional derivative to arbitrary fields. So like if we have a scalar field, so a function from the manifold to the real numbers, that's differentiable in some sense. Well, strictly speaking, in some sense, it's made precise when you think about coordinate systems, but let's not worry too much about it. So we have some function that's differentiable, and we take some vector, a tangent vector at some point p, and we can talk about the directional derivative in the direction v of our function f as simply taking a curve, a differential curve on the manifold that satisfies that at p0, so at 0 it's at p or point p, and the derivative of this curve at 0 is our vector v. And so you could like build arbitrary, like any curve that satisfies this is enough. So this curve is just has a single parameter t. You can think of it as time. And we have f of pt is just then simply a real function, right? And so we can take the derivative of that. And so we have the standard definition of the derivative, like limit as t goes to 0 of 1 over t of f of pt minus f of p0. And so that works. Now, can we generalize this for other types of functions? And especially, like if we have a vector field or a tensor field, can we do the same? And turns out the answer is yes, but it will require a bit of complicated machinery. So, for example, if we try the naive approach of simply like trying the same stuff and seeing if it works, right? Let's say we have a vector field x, and we'd like to take like the partial derivative of x along some basis vector dxj. So we can sort of try and extend the definition as simply taking this is the limit as this delta xj goes to 0 of my vector field evaluated at xj plus delta xj. Again, don't forget, like this is a vector, so this is a basis vector ei, so this xi means the ith coordinate minus, and so we're doing this minus xi at our original point, so just xj. And here we have a problem because these two objects do not belong to the same space. They're both vectors, but they're not vectors at the same point, so they're vectors from two different vector spaces. And so if we try to do this, we have a type error. And so we need somehow to be able to translate like this vector here all the way to the space at the tangent space at x plus dx. And we'll call this way of translating, like both translating the like linguistic sense and in both the geometric sense of you move around. So we'll be calling that parallel transport, and we'll see the precise definition later. But keep in mind that it's the idea that we have this tangent vector at our base point here. We've moved along some direction in parameter space, and you have a new tangent space, and we have another tangent vector, and we'd like to be able to move along this vector so that it sort of stays tangent to the curve. Now, this is where the actual reading was not super intuitive, so I kind of ended up ditching it in favor of my old differential geometry course. And the intuition is that, let's say we have this x tilde that's supposed to be the parallel transport of not v but x. So let's say x tilde here is the parallel transport of our vector. So we have the original vector at x, and we've somehow moved it over to the tangent space at x plus dx, and so we call it x tilde. And we'll ask it to have a few constraints and conditions. The first one being that so here we're comparing just coordinates, right? The ith coordinate of x tilde minus the ith coordinate of x at the point x should be proportional to delta x. Roughly speaking, what this means is that it should be sort of linear or an affine map. And the second condition is that it should be linear in this vector field that we're moving over, translating over, right? So if we have like the parallel transport of xi plus yi, this should simply be the sum of the parallel transport of both of these. And if we impose these conditions, it's not too hard to find that the parallel transport may be something of the form x tilde I is the old coordinate, so xi x, plus some correction it's a bilinear correction, so it's because it depends linearly on the displacements delta xj, and we have this and depends also on the coordinates, but all the possible coordinates back in x. And we have sort of this linear map or bilinear map that takes both these xk and these xj's and outputs something for the ith coordinate. So we have the new coordinates are the old coordinates plus some bilinear correction. Using this, we can actually define the so-called covariant derivative along the basis vector j. So I'm not always denoting everything, but whenever you have like this subscript j, it means the like directional derivative alongside the basis vector j. So then this is simply the limit as delta xj goes to 0 of my xi x plus dx, so that's the vector at the x plus dx, plus the parallel transport of I over delta xj, and in the limit this simply becomes the partial derivative of xi relative to the jth coordinate vector plus this bilinear correction. And so we've defined in some sense the directional derivative. Now, before speaking more about these coordinates, it turns out that this object that we've defined, this covariant derivative, we can define it simply axiomatically, and it's what we have here. So we define an affine connection as some map between two, so that takes two vector spaces or vector fields, sorry, and gives us a new vector field. So if we take two vector fields x and y, it returns a new vector field, so-called the covariant derivative of y along x, and it must satisfy a few conditions. But note that these are axioms. So any object that works, that satisfies these connections, is a connection. In practice, we can find many of them. So roughly, it should be linear in the main argument. So if you're the covariant derivative along x of y plus z is the covariant derivative of along x of y, and the covariant derivative of z along x. Similarly, if we have like two, so it should be linear in terms of the direction that we're deriving it. So again, then these next rules tell us about product. So the first is simply if we have some scalar field that multiplies x, we're just multiplying the covariant derivative. And then that last one is actually interesting because it tells us that this covariant derivative should act like a derivative in some sense, because we're like, if we think of this nabla x as a directional derivative, and then we're taking like a scalar function times a vector field, we have a product, and so we would like this to satisfy the product rule of the derivative. And so this is what this axiom is saying, that we're separating this as the directional derivative along x of the scalar field f times y plus f times the covariant derivative of y in direction x. Now back to connection coefficients. We have this rule of these covariant derivative of, in direction j of the ith basis vector, and this gives us the expression of the connection coefficient. So it basically tells us if I take my ith basis vector and I transport it parallel transport it in direction ej, okay, it becomes a new tangent vector and I can express it in the local basis, and so I need these ek vectors, and so that's why you have this object that gives us the expression of our vector after parallel transport. And using this, we can actually compute the covariant derivative for arbitrary vector fields. So let's say you have x and y, two vector fields. Simply by applying the axioms we've seen previously, we can turn the crank and we get that the covariant derivative of y along x is this expression that gives us, so we have the xi's times the partial derivative of y along the the local, so the vector basis, the tangent basis, plus this connection coefficients term. Okay, so far so good. Any questions? I guess not. So yeah, so strictly speaking, there's a bit of confusion between the connection and the covariant derivative. Sometimes they're used interchangeably, but we'll say that this operator, so nabla along x, we'll call that the covariant derivative along x, and for just nabla without anything, we call that the connection. So this operator, the covariant derivative, it acts on tensor fields. So we already, so by definition, or if you just turn a crank, we see that if we apply it to a scalar field, that's simply the directional derivative, so we already know that one. For a vector field, well, that's how we defined it, so we also know the formula. And then for arbitrary tensor fields, right, so remember we can express any tensor as a sum of tensor products of lower tensors, and so in doing this we can sort of get some recursion going. So if I take the covariant derivative along x of this tensor product of t1 times t2, well, we also want the product rule to be true in this case, and so that's essentially what we're doing. So we're taking the covariant derivative of t1 tensor product t2 plus t1 times the tensor product, the covariant derivative of t2. And we can also do this for covector fields, so one forms. I don't think we've talked about this, but the idea is that like this omega object is just a field that returns a covector, and so if you can apply it to a vector field to get a scalar field. So like this expression, so angle brackets omega applied to y is just a scalar field. And using this, we can define what the directional derivative should be for these form or covector fields, and using this you can define the covariant derivative for arbitrary tensor fields like that have both covariant and contravariant indices, but the expression for that is a bit too ugly, so let's not look at it. Okay, now an important fact to note is that these connection coefficients look like a tensor, but they're not. And the proof of that is fairly short, but so I've decided to give it. All right, if you pick two coordinate systems, so take xi and yj, and so we define, like, we have these gamma kij, the connection coefficients in the x coordinate system, and then gamma tilde for the same for the yj. Because we can convert from one coordinate system to the other by simply multiplying by the Laplacian, not the Laplacian, Jacobian matrix, so the partial derivative of xi by yj, we can convert this expression here back into the old coordinate system, And if we do this, okay, we have a few cranks to turn. What we end up is something annoying. We have that the gamma tilde is equal to this expression, which is actually what you'd get if this were a tensor. So like there is a tensor term, or a tensor change of coordinates, but then there's this additional annoying little term here that we can't really avoid. And so because there's this extra term, this means that these connection coefficients do not transform like tensor should, and so they're not tensors. So that's just an important thing to keep in mind, that okay, it looks like a tensor because it has like indices, but because it does not transform like a tensor, it's not a tensor. Okay, technical details aside, we can now do a few things. So we can now define what it means to be for something to like be parallel transported in some direction. So let's take a curve P, a differential curve of course, and take some vector field that at least it should be defined along P. Outside of P we don't really care. And we'll say that if the covariant derivative along V, which is the tangent to P, so like you think of the speed of the curve, we want the covariant derivative along the tangent to P of x to be 0. And if that's true, we say that x is parallel transported along P. I don't have a drawing for this one, but I'll have later. You can express it into coordinates if you want, but like how you should interpret this is that in some sense the coordinates of x are like constant relative to the tangent to the curve. We'll get a clearer example of this later, don't worry. Okay, so we can now we know parallel transport. We can also define a geodesic curve. So a geodesic curve is a curve such that its own tangent vector, so pt or p point t, is parallel transported along itself. So we have that nabla v of v is 0. Or in coordinate sense, we get this equation called the geodesic equation. Roughly speaking, you could imagine that geodesics are like special types of curves that just keep following the same direction and never move, so they have like no acceleration, they're not turning in the manifold. They might be turning because they're on a curved surface, but otherwise they're not turning. And also they have constant speed and so on. And then the nice thing we can do is, given a point on manifold and some tangent vector at that point, there is a unique geodesic that at that point that hits that point, it has that tangent vector. And so you can imagine taking this point P, P0 on the manifold, choosing this direction and just shooting a ray, shooting a geodesic in that direction, and we know that it always exists. Why? Because these equations are second order equations, and so because we have an initial condition P and initial velocity V, we have a unique solution, at least for some time, of these equations. Now, sometimes it's very useful to assume that you can take some tangent vector u and just shoot a geodesic of length exactly the length of u. So, right, so u has probably a length if you're in a Riemannian manifold, right? U has a length because there's a local metric structure on the tangent space. And so the idea is that we shoot a geodesic ray in the direction of u, and it should be the same length, geodesic length, of u. And we call this the exponential map, this map of taking tangent vectors to a point that's somewhere along a curve that we shot from the original point. And this exponential map is actually very useful for machine learning because we can use it to perform gradient descent on a manifold. If you want more details, read the blog post I posted earlier, but the rough idea is that if you take a scalar field on the manifold, so like our loss function, we can take its gradient by taking, so first we're taking the partial derivatives of f along the j directions. Then if we just take these partial derivatives, this is not a tangent vector, it's a cotangent vector because it's in the dual space of the tangent vector, and so we need to get back to the tangent space. And to do that, we need to multiply by the inverse of the metric. So yeah, this is something maybe I haven't made precise, but whenever we have like the symbol gij, this is like the inverse of the metric. So gij has indices on the bottom, and then this gij with indices on the top is the inverse matrix. Or you can think of it as the inverse matrix. So we multiply by the inverse of the metric to get back to the tangent space. That gives us a vector, but it might not be in the tangent space itself. There might be some extra term in, so we need to truncate by making sure that we're projecting this gradient back to the tangent space at our point. And then instead of taking like theta t plus 1 is equal to theta t minus eta v as we would do in normal gradient descent, instead we're taking the exponential map to just move in the direction of v by some distance eta t, so our learning rate. So yeah, more details in the blog post, but doing this we can actually perform gradient descent on a manifold and do all kinds of stuff. Now, at this point, you might be wondering, okay, that's fine and good, but where did the metric go, right? We like working with Riemann spaces, and we haven't talked about the metric yet, or at least we haven't talked about the metric in a while. And the reason for that is that the connection coefficients are arbitrary, right? Because the connection is just defined axiomatically, there can be many choices. But if we have a Riemannian manifold with a metric G, we can add constraints that make sense with respect to that metric. In particular, we can ask that the metric is covariantly constant, as in the inner product of two vectors xy should be invariant under parallel transport. As a corollary, that means that the norm of a vector and the angle between two vectors is also preserved under parallel transport. Now, if we translate this into equations, we get this expression that 0 should be equal to the covariant derivative along with some v of g of xy, and turn the crank. Ultimately, we get that the covariant derivative of g in the direction to the kth basis vector should satisfy this equation. So essentially we get an expression that binds both the metric and the connection coefficients. This is not enough to get everything, so we'll see later. So whenever we have this condition, we say that the metric is either a metric connection or a connection that is compatible with the metric. So specifically that these inner products are preserved under parallel transport. We can then show that the components of the metric connection or the connection coefficients, we can show that they are equal to this expression. So on the left we have something called the Christoffel symbol. It's this expression that depends only on the metric. So it's a 1/2 GKL, so inverse of the metric, and then these partial derivative of the metric, plus a term called, so this k here is called the contortion tensor. I don't really have time to give an intuition about what it means, but it's just this expression that depends on this t object that's called the torsion tensor, and then itself the torsion tensor is simply the like gamma kij minus gamma kji. And in general, like this right part, we can always say that it's 0. Or at least we can always find a metric that makes it 0. And note that by definition, this also means that the connection components should be symmetric, right? So yeah, if we ask the torsion tensor to be zero everywhere on the manifold, then all that's left is the Christoffel symbols part, and so we have just this expression. So really the nice thing about this is that, okay, this is a symmetric connection. It's also torsion free. I'm really sorry that I cannot explain what torsion free really means here, but maybe another time. It's also, of course, compatible with the metric, and so it's called the Levi-Civita connection. And it's usually the default connection that we use whenever working with Riemannian manifolds. And I think that there's always one. It's always unique, so it's also why it's nice. Okay, so now I'm going back to some of the stuff we talked about last time about these shortest paths. So we've seen like the geodesic equation in terms of the connection, but we also wanted to talk about geodesics in terms of shortest paths between points on a Riemannian manifold. And if you recall, right, we had 2 points P and Q. We wanted to define the distance between P and Q as the minimum for all paths X that smoothly go from P to Q. And we're trying to minimize this functional that's essentially this integral of essentially the norm of the tangent vector at the curve. So it might be not super easy to see, but like have x dot I, so the dot on the top is meant to indicate the temporal derivative. And so if you've seen some of the episodes of when we did that in the functional analysis reading group, you might remember the Euler-Lagrange equations, and these apply here. So we're trying to minimize some integral that depends on a smooth curve, and it all depends on the value of the smooth curve and the derivative of the smooth curve along the path. And stationary points, so the points that make this either a local minimum or local maximum, we can find them using the so-called Euler-Lagrange equation, which simply take this form. So the temporal derivative of dl over dx dot minus dl dxk is 0. So if we have n coordinates, we have n equations. Now, if we try to minimize this, it's a bit of an ugly expression because you have this square root. Luckily, we can actually get rid of it simply by noticing that. So let's say that we have this f, that's the quadratic part, and then L is taking the square root. We take the similar equation for f, and we end up with this term here that depends on so dl over dx dot times dl over dt. Notice that dl is the length along the curve, and a nice thing is that we can always choose to parameterize our curve or path such that it's arc length parameterized, so that the length at some point s is exactly s. And so using that means that dl over dt is 0, and so this expression is 0, and so we have this expression equals 0, so it also satisfies the Euler-Lagrange equations. And that makes trigonometry easier. So if we sort of expand the definitions and turn the crank, okay, there's a few steps, but we end up with something that is like the metric times dx squared I over dt squared plus this expression. And if you remember or squint a little bit, Like this part here is exactly the connection coefficient. And so we've actually recovered the geodesic equation that we had defined based on parallel transport. And so it's nice that when we use the Levi-Civita connection on a Riemannian manifold, then these shortest paths are also the geodesics obtained through parallel transport. So just pick a direction, never change from that direction, and keep a speed constant, and that's the shortest path. So nifty stuff. So now this is actually the final slide. The next one is empty. So if you want to give an example of the geodesics on a sphere, so remember, so I'm taking r equals to 1 to simplify things. We had computed the metric earlier for this. And if you just apply the formulas, you can find these connection coefficients. There's only 3 of them here, or really 2. And just using that, you can define the equations. They're not easy to solve, but after some manipulations, we get that the general solution is of the form a cos theta sinus phi plus b sinus theta sinus phi minus cos phi is 0. And these, it turns out, is simply the equation of the great circles on the sphere. So basically, circles that go through 2 antipodal points.